Why do we want to be using an IFU in the first place? And one of the main answers for that is because it gives us a lot of information that traditional spectroscopy just doesn't. So if you're interested in looking at a galaxy, say, here's an example image, for instance, from SDSS. If you look at traditional Sloan spectra, you've got a little fiber right down the middle of the galaxy like that you're getting your information from. You might be using a slit spectrograph to study a larger area of the galaxy, but it's still only a bar across the middle. And from that information, you derive everything you know about the galaxy in terms of its metallicity, star formation rate, star formation history, and whether or not it's got an AGN in the middle, what might be going on with the kinematics of the galaxy, etc. You can see from looking at it, though, that it's really not necessarily representative. There's a lot of the galaxy that you're missing. What you want to do is something more like this, where you can get spectra at each individual point across the object and use that to derive maps such as this one, where now instead of coming up with single quantities for the metallicity of the galaxy or the kinematics, etc., you can make maps of these quantities, maps of star formation rate, maps of the stellar age, maps of the rotation velocity, etc. So that's why we're interested in doing IFU spectroscopy in particular, because it gives us this greater variety of information, whether you're looking at galaxies, whether you're looking at planets, or what have you. So JWST has two of these IFUs, the MIRI and NIRSpec IFUs, and they jointly cover the range all the way from about half a micron all the way out to 28 microns or so. This is just an illustrative plot showing you the kinds of things that you get from that wide wavelength coverage. In the back, I'm showing you a typical spectrum of a galaxy. So you've got ultraviolet lines, optical lines, infrared Paschen, and PAH type lines. If you're looking with NIRSpec at something in the nearby universe, you'll pick up these near-IR lines, the Paschen lines, for instance. And with MIRI, you'll get this rich spectrum of PAH features out through the mid-infrared. And no matter what redshift you're looking at, then you still have these two IFUs working really very well in tandem with one another to give you a comprehensive coverage of the wavelength range that can even slide down at the very highest redshifts into covering the traditional rest frame UV. So another answer to the thing I asked a moment ago, though, why do you want to do IFU spectroscopy, is also because this is actually the only way to get medium resolution spectroscopy longwards of about 5 microns with JWST. So even though the MIRI instrument has a low-resolution spectrograph, it's a traditional slit-type spectrograph, it also has a slitless mode. That's low resolution, R of about 100 or so. So if you want R of a few thousand spectroscopy, you're going to be using an IFU to do it, whether or not you're looking at a point source or something else. So that's another reason why you might be using the IFUs on web, not because you're interested in the extended structure, but simply because that's the tool that's available to us to get spectroscopy in this regime. The two JWST IFUs are slicer-type units. That means that they divide the image on the sky up with optical slices into, you can think of them like lots of slits, all adjacent to each other on the image. Each one of these slits reformats the image on the sky and disperses it separately onto the detector. You can then stitch these together in the JWST pipeline software to reconstruct a three-dimensional data cube. There's something that has 2 spatial axes and 1 spectral axis, so you can plot the spectrum of each individual region within that cube. For the NIRSpec IFU, this is a 3x3 arcsecond field of view. It's located about here in the middle of the NIRSpec array, and as I mentioned earlier, it reformats the spectra from each of those slices, so they actually disperse across the detectors underneath these micro-shutter arrays. So it shares detector space with the MSAs, which is why we can't do both MSA and IFU spectroscopy at the same time. It's got 30 slices in that 3 arcsecond field of view, making each one of them about 0.1 arcseconds wide. There's a range of different spectral resolutions. The prism resolution is R of about 100, so very low resolution, but that gives you the entire wavelength range in one go. And there's a variety of higher resolutions as well. If you use these, though, then you need multiple combinations of gratings and filters in order to cover the entire NIRSpec wavelength range. If you look at what the detector data look like, here's what it is if you're dispersing these 30 or so different slits across the field of view. So here they are occupying the MSA region of the plane. You've also got the fixed slits dispersing across the middle of the detector. These are permanently open and can't be closed off. There's going to be a gap in the middle where those wavelength ranges cross between the two detector chips, though, so you'll always have a little wavelength gap in the middle of your spectrum. Once you run it through the pipeline and reformat it into a data cube, though, then you have something that looks like this on the bottom, where now you've got an image of your scene, and you can plot a spectrum of each individual spaxel within that scene, again with this little gap in the middle where the spectra cross the chips. For the MIRI IFU, the medium resolution spectrometer, it's actually 4 concentric IFUs that operate simultaneously. They're fixed with respect to one another, and they collect data at the same time. So here's what it looks like on the sky. The channel 1 IFU has the smallest field of view at about 3 by 3 arcseconds or so. This is that blue square in the middle here. And as you work out to progressively longer wavelength channels, they get progressively larger. So the channel 4 IFU, which is the one that covers around 20 microns, that's about a 7 by 7 arcsecond field that looks something like this. They jointly feed 2 different detectors. So on the first MIRI detector, then you have channels 1 and channel 2, one on one half of the detector, one on the other. And on the long wavelength detector, you have channels 3 and 4, also sharing that detector space. Similarly to NIRSpec, if you want to obtain the entire wavelength range, you need to do it with multiple grating settings. Unlike NIRSpec, though, these aren't sort of one after another grating settings you need to take. They're kind of interleaved with one another. So I showed you the 4 different channels that the MIRI IFU has. Each one of these channels has 3 subbands in it, an A, B, and a C setting. And this is what it looks like sort of schematically, where if you take A observation, then you have this blue piece here between 5 and 6 microns. This is in channel 1. You have a channel 2A wavelength range, a channel 3A, and a channel 4A. And similarly for the B and C wavelength settings. So you also have to put these multiple settings together with one another to cover the entire wavelength range, but they're kind of interleaved with one another instead. When you process it through the pipeline, you end up something that looks not exactly like a data cube per se, but perhaps more like a data pyramid, in the sense that the longest wavelength data has the largest field of view, and the smallest wavelength data has the smallest field of view. So you go progressively out to larger and larger dimensions as you go to longer wavelengths. So a couple things to keep in mind as you're working with IFU data products. The final stage products coming out from the pipeline are rectified combined data cubes. So they have axes of rate ascension, declination, and wavelength, and they're provided in units of surface brightness. That's done as a single step in the pipeline to avoid having multiple resamplings. Keep in mind, though, that data cubes are a convenience, but they have their limitations, and they're not necessarily ideal for all science goals. First of all, they're quite time-consuming to build. As you step through running the pipeline yourself, you'll notice that sometimes it takes quite a while for the pipeline to run through the cube build step. And that's something that we're working on speeding up, but it can still be relatively slow, especially for building big cubes. Individual spaxels in the cube, if you plot the spectrum of just one spaxel as opposed to a single spatial resolution element, you'll often see resampling noise. And that's coming about because the IFUs are severely undersampled by factors of many times in a few cases. You can also have covariance between the adjacent spaxels simply because of the algorithms you're using to reconstruct the data cubes from the individual samples of data that we had on the detector. And finally, there's a few corrections that you can't really apply very well in cube space if you're interested in looking at spectra of point sources on the detector. So there's a few things you might want to do differently, but cubes are a good starting point for everybody to be able to look at their data and get an idea what's in there and start doing science with the observations. The second products that we provide coming out of the pipeline by default are one-dimensional spectra. So these summary spectra are extracted from the 3D rectified data cubes by the baseline pipeline. And there's 2 ways it can try doing that. For point sources, where it knows the location of the source, it can do sort of classic aperture photometry, and it does it at each plane through the cube. So if you've got, say, this image from the MIRI IFU, here's a 5 micron image, here's a 17 micron image. You have a red aperture in this case. This is where you sum your flux. You do some correction for the background annulus here, and you apply a aperture loss correction that's in a reference file. You do the same thing out at 17 microns, but as the PSF grows, so too does your aperture, effectively. So it's effectively a cone aperture as you go in wavelength through the cube. If you're looking at extended sources, then the pipeline has no idea what the structure of your extended source might be. It could be anything within the field. So in this case, what it does is it just sums the entire field of view for you by default. So everything that's in the field, it will sum up and add into your final one-dimensional spectrum. What that means, though, is that because the fields of view differ from channel to channel, you can sometimes see jumps between channels if you're looking at extended source spectra. They're not telling you anything about, say, jumps in your source. They're just saying that because your field of view changed, the extraction is now being done over a slightly different region. So it's good to be aware of when you're looking at the outputs.